Hello, happy New Year, everyone. This is our first session in the new year. I hope you had a nice holiday. I had a little bit of that. We're in Lagos, so went to the beach. Was it the good beach or something like that at Lake? We had fun. And some clubs too. Yeah, I hope you had a nice time wherever you are, whatever city you are, and you rested for a while. So we are back. I hope you had a nice holiday. Yeah, we are back and we're going to Bitcoin theory proper. If you had noticed, we made an announcement before the break about people that couldn't join early, and we extended it for them to join. And that's the last extension we have. So at the end of this period, the pre-course will end. And everyone that had gone through the Bitcoin theory and done the assessments when they are unlocked will move on to phase 2. So let me remind you, tomorrow we are having a guest speaker. He's from My 2 Cents, part of the BSV ecosystem. They've deployed some real app that works, so it's interesting to have him take one of the courses tomorrow. And maybe after that, we'll take a look at what they have done, see how you guys can mirror that in this cohort. So let's jump right in. I don't know, my machine is a bit slow today. I think I have a lot going on. I'll just manage it that way. Okay, I can play something. Oh, it said my screen sharing is paused. I'm not sure why. Oh, yeah. So hold on, let me stop this share and share my entire screen. Sorry about that. Just one moment. Okay, I'm no more sharing anything, so I'll just go ahead and share my entire screen. Share. Okay, back again. Okay, I hope you can see my screen now. So this is the main course. What we did before with JavaScript and Golang are just to give you the tools you will need when we go into Bitcoin scripting, right into this in the middle of this course. But today we are looking at the main thing. This is what everyone must have gone through. If you're watching me today, I mean, if you've been on the Telegram group, I suppose you've gone through all this. So what I'm doing more will just be to take some silent points and we go through them. I've got many questions from people, which I documented some of them. So as is the usual stuff with this course, we're just going to read through the abstract. 1 minute, please. Yeah. So the Bitcoin paper, you already know, was released by Satoshi Nakamoto. And this is the abstract. I'll read through. A purely peer-to-peer version of electronic cash would allow online payments to be sent directly from one party to another without going through a financial institution. Digital signatures provide part of the solution, but the main benefits are lost if a trusted third party is still required to prevent double spending. We propose a solution to the double spending problem using a peer-to-peer network. The network timestamps transactions by hashing them into an ongoing chain of hash-based proof of work. forming a record that cannot be changed without redoing the proof of work. The longest chain not only serves as a proof of the sequence of events witnessed, but proof that it came from the largest pool of CPU power. As long as a majority of CPU power is controlled by nodes that are not cooperating to attack the network, they will generate the longest chain and outpace attacker. The network itself requires minimal infrastructure. Messages are broadcast on best effort basis, and nodes can leave and rejoin the network at will, accepting the longest proof of work chain as proof of what happened while they were gone. So the entire of this course will be dissecting abstract. So abstract is just one part of it. We have the introduction. We have everything mentioned there is a topic of its own. So I'll do more of a surface going through. In subsequent lectures on this introduction to visual theory, we'll have to now go in depth for every single sentence in this abstract. So a purely peer-to-peer version of electronic cash would allow online payment to be sent directly from one party to another without going through a financial institution. When he released this white paper, way back in 2009 or so, that's when we had the global financial crisis that affected a lot of things. Yeah, I still remember that vividly. At the time, I used to go offshore, maintain IT infrastructure on a vessel somewhere, And I remember that during that period, the whole financial crisis thing, the guys managing the FPSO, they had to pull out because of some issues. So it was quite destabilizing. Lots of businesses left. So that was a problem. We had a big financial institution came crashing. They had to be bailed out by governments all over the world, right? So at that point, that's when he released this paper. And now this paper is saying that it is possible to have an alternate version that involves peer-to-peer, okay? You can actually transfer peer-to-peer cash and make payment from one party to another without going through any financial institution. That was the cash word there, no financial institution. I want to make this statement. The purpose, there's something in research, in science in particular. You might be trying to solve one problem, right? And when you get that problem, now find that it had bigger implications. Take, for instance, in biology, they have this CRISPR. Someone was just studying, why is it that some bacteria, when they get infected by, let's say, a fungi or something like that, okay, their system takes care of it. It doesn't propagate. So they were trying to find out, how does this happen? And in trying to study it, they come out with CRISPR. They found how those bacteria they have something that's already encoded, some piece of DNA in them. Whenever it sees that stuff, it knows what to do. It synthesizes what will go and just cut that gene off, remove it and replace it with what is good. And from there, now we have CRISPR, which they now use to do lots of stuff in plants and in animals. So that's how research and science works. So this guy, he was just more interested in solving the cash problem, where financial institution will not be, will be taken out of the whole equation. That's why we mentioned peer-to-peer electronic version of cash. But I want to say this, in this course, actually, we're looking at now more implementation, application of Bitcoin blockchain, not just for cash now, all right, but to solve enterprise problem, identity problem, all right, sock fake, whenever you're having fake things everywhere, fake certificate, which one is real? You studied in Nigeria, you go abroad to make, continue your study. There's issue of sometimes just trying to verify your certificate, going back and forth with the union and everything. Before you lose the opportunity, right? So it's a big, huge problem out there. Birth certificate, there are still controversies. Was this, was that not that? So this can solve these problems, okay? And many, many more. So when we look at the original implementation, which is just how to transfer cash from one person to another, But we now found out that network he built, the solution he provided, can do much thing. Anything you don't need a third party, you can put blockchain. Look at it again. He said peer-to-peer version of electronic cash, okay, that will be sent directly from one party to the other without going to a financial institution. So I want you to think about this. If you think of any solution right now that requires middlemen, just know that you can bring in blockchain there. That blockchain can remove the middleman and boot peer-to-peer. That's it. So have that in mind. Anywhere you have middle people coming, is you have to go through an intermediary to solve any problem. Just know that you can fit in blockchain in the middle. It takes care of that completely. So when you bring it, look at how best to implement this, you know. So that's the whole point of this paper. Yeah. So in a normal traditional financial institution, what are their roles? Now we have the central bank. Every country has their own bank, right? That regulates, distribute their currency and bring out policy. Sorry about that. I have a power failure and I was actually I'm not sure if you can hear me now or see me now. Let me check. Okay, it seems I'm back online. I'm sorry about that. I had a power cut, power failure rather, and I was using fiber optics, you know, so I had to switch over to Wi-Fi now. Regular that has power won't go off with power console, but this connection, I hope is fine. Okay, back to my presentation. For 1 minute, please. I'll have to share my screen again, I guess. Okay, sharing everything now. Back to this. All right, so we're looking at the role of traditional financial institutions. So we have central bank, they distribute currency and they establish monetary policies all over. We have our own, we have the Central Bank of Nigeria, right? And yeah, in fact, they're distributing new currency as we speak. The new Naira, you know, some denomination where the 1,000, you know, the higher bills, you know, they made a new version of it and there's a deadline beyond so period. You cannot spend it. You can still take it to the bank. So these are what they do. So we have a new currency now and they have policies relating them. They even have policy related to cryptocurrencies, as we know, right? So that's the work of central banks. They do that. They are the intermediaries. If you're ever going to send money to an outside the country, sort of, you know, somehow you have to go through the clearinghouse of the central bank to have that, to make that to happen. So that's the thing. They are the trusted party. If you're having any dispute right now, you have somebody to fall back to. Some people have had complaint. Their banks, did some charges, didn't do some reverse. They will go and tax central bank, blah, 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 and say, hey, this bank did so stuff, right? And then the banks, knowing what the implication of that they are regulated, they come back and they fix whatever problem it is. So yes, they are there, having regulation is very good, because without regulation, there will be problem. You can, both the consumer and the consumer and the producer, they will be in jeopardy. But when you have regulation, it's good for everybody. It's good for you, the product producer, because you have an environment, a law with which you can operate, right? And you're comfortable as long as you meet all the laws, you know that you're doing the right thing. And the consumer too, if you agree about anything, you have where to go to. You have the central bank, you go, and they're there to arbitrate and solve the problem. So that's the traditional part, okay? And then we have the commercial banks, and they provide all kinds of services, right? The primary ones are to accept deposits, and they offer loans. So most of us, we have money in deposit in our commercial banks. Yeah, they do that. And sometimes you also they give you some loan with some interest on them. And they have other secondary function. For example, you transfer funds between one branch to another branch. You do that through the banks. And periodic collection, you're running something and you're collecting money. Like, you have collections you are getting from people, and they can handle that. Payments too, you want to pay for your services, your utility bills and all stuff like that. You can use banks to do that. You want a letter of credit, you want to do some transaction with a foreign firm or even in Nigeria here, but they need a guarantee that from a financial institution, because it's trusted, right? They know, okay, if we get this guarantee, whatever defaults, we know who to hold. So they give all those letter of credit, right? And then you also have your FX, foreign exchange. The only way you can move foreign exchange between across borders is using your bank, through the bank. So the thing is, they are established by law and they are regulated by the law. So that's the normal things we've known, right? We have the banks, they are backed by the law. The law, even they are also regulated by law. I can remember during the Yaradua administration, I think Soludo was the CBN governor, so he wanted to shift the zeros in Naira. Let's say we have 1,000, want to shift it backward, a little bit. And he was gearing towards that, made all the arrangement. But later on, the presidency found out, but from their own perspective, this shouldn't go through. So they canceled it and it didn't go through. So even the banks are being regulated. So that's how it works. The law is the main thing here. Now, but the Bitcoin blockchain, as proposed by Satoshi, what he did was the whole thing about the banking thing, it takes it out of the equation. That's what it does, out of equation. So in Bitcoin, money is exchanged peer-to-peer using the Bitcoin protocol. So in place of banks and all those institutions, we just have a protocol, and protocol is, so mathematics cast already. They worked out all the math, and it's supposed to do what it's meant out to do. And you can audit it. When you audit, you could see, yes, this, that happens there. So it takes off the whole trusted third party and say, people can actually transmit peer-to-peer. I don't know who you are before. You're in Adamawa State. I'm in Lagos State, as I am right now. I can actually transact with you in Adamawa State without actually passing through a financial institution. I want to reiterate again, this is how the Bitcoin, this was the main purpose it was, set up. But like I said, in this course, we are focusing on the applications in enterprises, in government, because there are lots of government here right now that need blockchain to streamline them, to solve those problems, right? And that's what we are focusing on. Someone asked me a question on Telegram. Say, oh, so are we going to be creating coin? I said, well, no, we are not creating coin. That's not the purpose. The purpose is to build applications, okay? For experimental purpose, you could do whatever you want to do, but the purpose of this, all the project we'll do here will be at solving problems that we have right now. We still have some farmers in remote areas that do not have access to banking, all right? So how can we help those people? CBN is taking the lead already. They've deployed the e-Naira, okay? The e-Naira is a cryptocurrency, yes? And so the CBN is also propagating the cryptocurrency, but as a regulator, yes, you have to manage, your borders very well, manage your policy, and that's what they are doing, right? So it's not like, I'm sure it's not going to be forever, okay? But as soon as things takes shape, as it's taking shape all over the world, everywhere in the world, there are still governments are still, studying the whole blockchain-related thing as far as crypto goes. So that's why we are not concentrating on that part, but we are looking at other solutions that we need right now to help solve problems in businesses and in government. And that's where we come in. So this blockchain allows peer-to-peer. If you look at the diagram there, you see the guy on the coat, on suit, and you see the lady at the other end. So the guy on suit can transact with the lady at the other end, just the two of them without any trusted third party. I use that word trusted. There's a reason I use trusted. We'll see that in a bit, why I'm using that word trusted third party. Like I said, banks are trusted third party. You could make a transaction right now, and you could mistakenly, you are sending money to somebody and mistakenly send it to another person. You are looking at the name, right? It goes to that person's account. Oh, what do? You rush to your bank. Hey, I made this so payment. It went there, right? They look at it, so they can actually freeze that money, seize it, resolve the issue, and the money comes back to you. They are the trusted third party. But in the Bitcoin blockchain, there's no trusted party. What you have is the Bitcoin protocol. Once the scripts are right, when you do your you set up your transaction, okay, and they are all valid, they go through. And once they go through, that's it. You cannot reverse it. Right? It's one way. Once a transaction goes through, it's done, it's done. The important is that it's valid, okay? And yeah, it has to be valid, okay? Once it's valid and they checked out, it's genuine, you haven't used it before and all those, it goes through and that's it. So peer-to-peer cash, we are still on that. Now, wallets are what we use in blockchain. In normal regular banking, you have so many ways you could do that. You could have, right now, there are tons of ways. You could have your debit card, right? Or credit card, as the case may be. You have your app, right? You can log into your app, do your transaction. You can use now CBN is pushing very well that we have to go cashless. And it reflects in all the regulation that have been coming out. So everything has to be cashless, not moving money around. I mean, physical cash, right? So yeah, you use all those things. You have your checkbook, you can write your check and all, but in blockchain, all you need is what we call the wallet. So wallet allow users to create transactions that sign ownership records of digital coin and assign them to new owners. Now, wallet is not a physical thing. It's not like we call it wallet. It's just for, I think, for semantics, just for what purpose they call it, okay, it's a wallet. But actually, what it is a data structure used to store and manage users' keys. That's what it is. It's just a data, what it does is just store your keys. I think in the next slide, we're going to talk about keys. So there are different types of this wallet. You have the desktop full node. You can have this on your desktop. If you install a full Bitcoin node, for instance, you can have wallet in it, right? You can have wallet running on it. So it's a full node. You also have the mobile lightweight wallets. They are mobile, they are lightweight in the sense that they don't have all transaction in the Bitcoin. No, they might have transaction that have to do with your addresses. Any transaction have to do with your address will be stored locally there. Then if they need to verify anything, they can hop into the network and there's a way to do those verifications. So they're lightweight. Think about it. A full Bitcoin node, I'm not sure of the number, but I'm sorry. It's in gigabyte. It's something about 4 gigabytes or something like that in that region. That's if you want to run a full node. Of course, you can't have that in your regular phones, all right? So that's why we have the mobile lightweight wallet. And then there's the web ones, the third-party wallets. They use APIs to communicate, right? And then we have the hardware wallets. Those ones, they are not soft, they are just hardware, piece of hardware. You take them offline. They are the safest way to store. For people that have digital assets, it could be NFT, it could be anything, whatever digital asset you have on the blockchain, and assuming it's worth a hell lot, the value, and you don't want to mistakenly, lose it or something, you could use the hardware wallet to store them. And again, this is not the in-depth of it. This is just abstract I'm doing. So we still have, along the course, we'll have to go through all this, see how you construct wallets. Hopefully during your project phase, I assume some people will want to build some wallets. I assume so. And when that comes, you need the in-depth part of it to be able to understand how you can build your wallet, using the existing protocols, because there are standards. Whatever you want to build, you have to select, okay, which standard am I building on the SegWit? There are different standards. So you select whichever one that feel works best for your solution, and you can build your own wallet. And yeah, and we encourage people to use it. Yeah. Okay. So, I've talked about the types of wallet. Okay. This will be familiar to most of you. So in this course, we BSV implemented the, is it Learn to Earn? Yeah, the Learn to Earn program. So what happened in partnership with SendB is optional in this program. If you want to earn as you learn, you have to install the SendB wallet, for example, right? The SendB is a project under BSV ecosystem. Yeah, I think that's why we're using it. So if you want to earn, you have to install this, tie it to your Fifth Work account, so that when you start doing your assessment, as you are doing your assessment, you're earning, and it's going to your wallet. And we'll still have more courses to do in phase 2. So as you are doing both the phase 2 courses, the more you learn, the more you earn. So that's an example of a wallet. You see what happens here? We just have these two buttons, the simple thing, receive and send. Under receive, when you click the receive, you see your address, right? Your public key is actually a public key. We'll see a diagram of that very soon. So you see your address there. If you want to send, it allows you to put the address of the person you are going to send to. Because those things are, 64 hexadecimal numbers. Sometimes they are tiny, you can't see them very well. Sometimes you have this QR codes. You just scan them. When you scan them, you just put in your address into it. And sometimes when you pull it in, you bring in some extra character. You have to be careful. Sometimes you bring in it, you might put Bitcoin column, then blah, blah, blah. You have to remove the whole Bitcoin column thing. If you are using the scanner, always make sure that when you scan, any extra character that comes in, you take care of that to have so if you scan it and I tell you it's invalid, probably there's an extra character. Just look through towards the end or from the beginning. Check, that's where it should be. At the beginning, you could have something that was added, or at the end of it, you can have question mark and blah, blah, blah. So remove the question mark and blah, blah, blah. Once you do that, yeah, you should have the address, whether your own or somebody you're sending it to. Okay. So if you are using something like a wallet, like I said, that's what you use to interact with the blockchain, the wallet, right? And let me say this at this point. Okay, I'll get to that. So if you're using a wallet, for security reason, it stores your keys. In fact, what the wallet does is to store your keys. That's all it does. Wallet does not store anything. Let's say you're in a blockchain and you have BSV, what so X of Naira. You have a Bitcoin, what so Y of Naira, right? You have so many digital, you have NFTs too. When you have all these things and you say you store them in your wallet, what you actually do is to store the keys, the private keys that can unlock those transactions, those digital assets. So if you're on the Bitcoin blockchain, for instance, your private key will all your assets are on the blockchain. They don't leave the blockchain. They're in the blockchain. Only thing your wallet does is to interact with the blockchain and provide your private keys. So the wallet can construct your private key independent of the blockchain. Like I said before, it's just programmatically, just a data structure that stores key. That's what the wallet is. So when we say wallet, I don't think that all those things you have, you store them inside the wallet. No, your wallet have the key. So if you add any new asset to your wallet, what your wallet does is to construct is to have the private key okay, that can unlock that asset. That's what your wallet does. And that's why you can have a wallet that is not even connected to the internet, cold wallet, right? It generates its own private key without even interacting. So normally, these private keys, you don't normally see them. You don't see them. Or they know if you're just a regular user, you don't see those private keys. Okay, they are converting some other things, but you can use mnemonics to save them. So what are mnemonic words? There are 12 to 24 English words selected randomly by a wallet software. You know, they are used as a basis for keys that are generated by wallet. So if for some reason you have wallet in your phone, maybe your phone got corrupted or you even lost your phone, right? How do you recover your asset? So that's where the mnemonics come in. You can use them to restore your transaction and any digital asset you can have in the wallet. Usually there are 12 to 24 words, depending on how many bits. If you're using 128 bits, you have 12. If you're using 256 bits, you can have 24 words. I think the most common one is the 128 bits, which give you 12 words, mnemonics. So when you set up your SendB account, for example, I know it generated some random number words for you. Say, hey, write these words down somewhere, right? So if you get another phone, when you open it, it asks you, do you want to recover or you want to make a new? You say you want to recover it. Once you ask those things, we'll see how the recovery process goes. So here is an example of what happens with a mnemonic. See how it's generated. So it takes entropy, just disorderness, you know, or entropy, disorderness, the rate of disorder of a sample. That's what we learned in chemistry. First time I met that word. So here too, so you just take a 128 bit. You see, we're doing 128 bit in this case. Like I said, 128 bit will give you 12 words. But 256, between 128 bit, you have 15 words, you have 16, you know, depending on the number of bits you are using. But it goes from 128 to 256. You can have any number of bits. If you're making your own design of your wallet, right? So for a 128 bits, so it just takes a random number, generate a 128 bit random number, right? And, you know, pass that through SHA-256. That's what it does number. To look at the diagram, I'm just explaining, okay, here is it. So number one, you just generate a random number. It doesn't mean anything, but there are ranges, you know, that's how it selects it, make sure that it falls. Most time has to do with prime numbers, something like that, right? So it generates that entropy. Then number two, it passes it through SHA-256. We'll know what SHA-256 means in a bit, in a little more bit. I'll show that. So it goes to SHA-256 and adds a checksum bit, you know, some number to checksum, confirm, make sure this is all right. It adds some bits into it. And then into the entropy, that's number three. Now it splits them into 12 words, into 12 columns. Let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we see these 12 segments, each of them of 11 bits. So what it does now, in these 12 segments, each of these segments will now be mapped. You see? It maps this entropy into a word list using the dictionary, normal dictionary of 2048 words. When they map it, it corresponds to a particular word. So here you have 0, 0, 0, 0, 1, 1, then the remaining bits are 0, maps to army. That's what it does. You know, first of all, it's a random thing. You know, it didn't select army before I started. No, it's just from the random stuff, add some checksum, then split them out. And each of these bits here represents a word in the dictionary. So you see here forms army. So the first word here is army. It comes, pick the second word here. It maps it into the dictionary. It maps somewhere. In this case, it was a map to van. And the third one, map to defense. And it has to be in that particular order. So when you write out your mnemonics, you must have to follow the order. If you don't follow the order, if you are giving it back or you're putting it down, you don't follow the order, it's as good as gone, because except you do a lot of permutation to find out what it is. And believe me, how many words? 12 words? You only permutate that. That's a lot based on number of words that are here. So that's what it does actually. When you do all this, it will now give you the words you will now take and store those words, right? Okay. And it can also get, so when you are restoring when you are trying to restore, maybe in a new device, it will also take those words and do a reverse thing. I think, let's see the next slide here. Yeah, so from the seed, you can also go back to your mnemonics. So what happens here, there's a key stretching, there's a function called the key stretching function. It accepts two values. It takes your mnemonic keys, you put them in the order. We have Army, Van, blah. If you remember, this is the order we have it there. Okay. Then when you are doing the mnemonic, you can add salt to it. Salt are just like a random word. Only you know. You can. It's optional. It's not a must. You can add a salt to it. Just like when you're doing in a computer, when you are trying to log into another computer remotely, maybe using terminal, you do SSH, right? So when you create your keys, sometimes your key will ask you, do you have a sort, a paraphrase, a passphrase? If you put it, so whenever you want to log on, because if you're using keys to log on, your keys, you don't need to put your password. You just say SSH and user at wherever it is, enter. It will check if the keys are okay. It logs you on straight. But if you have a paraphrase or password, passphrase in it, in addition to authenticating you using the keys, it will ask you to put that passphrase, right? So this function here takes two arguments. The first one is your mnemonic, and the second one is the passphrase, which is optional. Most time you just have your mnemonics running here. So when you do that, now the second part, the entropy is then used to derive a longer 512-bit seed through the use of the key stretching function. It's not a function. They've written all this function already. It does what it's supposed to do. And from there, the seed is produced, and can use it to build back your wallet. So it goes one way, it comes out on the other way. So it's very important. If you're doing anything in the blockchain, please, if at the end of you want to design wallet, it will teach you all the rules, all the good practices, all the do's and don'ts in creating wallets. And you also see different implementations of wallet, right? There are some wallets that are aware of, because Bitcoin is a public blockchain, yes, we know. But yeah, it's public, nobody is in charge, but there are a group of, like, the miners are there mining, there are people writing the program. So there's a way to propose improvement. There has been many improvements already, like in the addresses, there have been different improvements. So they come in and they pass through all kind of processes, even the miners are involved. During mining, they can vote, because it's more like the majority carries the vote, because it's a public thing, right? So yeah, so there are certain ways you get these things done, and that's part of thing you will learn in the course of this program. So this mnemonic is very important. If you lose that, you lose your assets. In a traditional system, if you lose something, you don't know your password, you try so many times, you can just walk into the bank. Hey, I'm here. I mean, I've tried this, it's not working. They could actually say, okay, bring your fingerprint. They'll manually put it. That's you, right? They could physically do some checks, and yeah, you could technically get your stuff back, right? But in the blockchain, because we don't have, it did away with the whole third-party trust. It doesn't trust any third party. The protocol is it. Protocol does everything. So if you lose this mnemonics, then you're as good as gone. All your asset for that is gone. So here are some rules about storing it. So if your mnemonic is not protected enough, it will be at risk of being stolen. So if you just carelessly store it somewhere, right? Just write it down somewhere on your computer, or wherever. Yeah, someone can see it. Now, if you're doing this course, you already know that mnemonics are some 12 words. You can even write a program. In fact, I tell you one thing. there are programs that could be installed on your machine, maybe transmitted through, malware or anything, and you start looking for fingerprints, fingerprint that resembles seeds, seed phrase, and can grab them. And program also can, try every combination of all different wallets to see whether this works. So even putting it down somewhere in your laptop or your desk or machine is not quite safe place to put it in. Okay. So if you're careless about it, you could lose it. If it's stolen, that person becomes you. Remember, in the blockchain, your identity is your key, your private key. That's your identity, your private key. Now, sometimes we had stories of an exchange was hacked, and you say, but it's blockchain. How come they hacked an exchange and took my stuff? Well, let me tell you what happens. In a centralized, when we talk about the Bitcoin blockchain, it's decentralized. There's no central authority. So some people came up with ideas. Okay, you know what? We can help you manage all your assets. They're called centralized exchanges. There are examples of them. Okay, we can help you manage your assets. So you come there, you create an account, username and password. They even do your KYC, to conform to the laws, the regulatory authority, wherever they're operating. So when you set up something like that, your private key is being managed by the central exchange, not you. Yeah. Now, let me take that again. If you have your wallet, like, that connects directly with the blockchain, is decentralized. It has nothing to do with anybody, just you. Everything depends on you. Okay. But if you go to a centralized exchange, and why would you go there? Okay, yeah, they offer so many incentives. For example, it's easier to trade there. It's easier to do your NFT, mint it, so you have an account there. Just having that account means they're managing your key. And if for some reason it's hacked, right? Because when you log on, remember when you log on with your username and password, you still have access to your assets. So if that central exchange gets hacked, and they'll clear everything. We have so many cases. FTX is a more recent thing, though it went down due to so many other issues, not just that it was being hacked anyway. But what I'm trying to say, centralized exchanges, once it's centralized, you still have the problem we had before we say, hey, let's do away with the whole third-party stuff, all right? But in a real decentralized system, everything is you, your security, everything, you manage everything. So a common practice is for people that have, different kind of assets. You could have very few of them in a centralized exchange, just something you could, run around for daily. Then the major assets, you put them in a decentralized wallet. Like you can create a wallet when we are done with this. You can make your own decentralized wallet. You can use to store your own private stuff. But again, if you protect it too much, you stand the risk of losing it permanently, right? Yeah, let's say you have a 12-word character, 12 words that form your mnemonic, and you're writing it down. They say write it sequentially. You write the first one, second one, third one. You take the last one and put in the middle. You just jumbled it like that. Hey, you're at risk, because at the end of the day, 2 years down the line, not even 2 years, 3 months down the line, you never use it. If you come back, how did I do this? You don't know anymore. So you try to be so strong about it, you could actually permanently lose it. So what do? You balance the risk. And the common method is you write out 2 copies of the mnemonic phrase on paper, right? With each of the words numbered as the order matters a lot. You number them, then you store each copy in a separate secure location. You could have in your drawer at home, another one a private proof, maybe one is in your video. I'm just saying, I'm not saying this is what you're supposed to do. But as we are taking a course, that's part the essence of going through a course. You look at all these pros and cons, and if you are talking to somebody, it's okay, yeah, I've been through this course, I understand what that means. Okay, so you make 2 separate copies of them and store them in different locations, just so if something happened to this one, the other one is also available. So that's about mnemonics. Yeah, your private key is your identity. Example, in the metaverse, when you go into the metaverse, your private key is your identity. If somebody takes that your private key, that person has stolen your identity and it's gone. And it's decentralized. Remember, there's no third party anywhere to go say, hey, blah, blah, no. So it's all on you to do that. So when you're designing your application, please bear this in mind when you're doing your project work. Okay. I've talked about keys a lot. Keys. So what are these keys? All right. So keys, they come in pair. We have the private key, which is a secret one, and we have the public key. Public is public. So keys can be generated and managed by users' wallet software without reference to the blockchain or access to the internet. I said this before. So your wallet actually handles your keys. Now, the public key is used to receive funds, and the private key is used to sign transactions to spend the fund. So when you have any digital assets, be it in the metaverse, be it an NFT, let's say you're an architect, okay? Because right now, a lot is going on in the metaverse. People that are architects, it's a good time for them now. At Base University, we revamped their curriculum already for the architecture department, to include metaverse, NFT, blockchain, right? So the idea is the metaverse, and people will build in the metaverse, there'll be structures and all these things. And of course, you need to be a qualified architect, to submit the drawings and, all the structures, everything. So a lot is going on there. And you have this wonderful architectural stuff you made, and you sold it as an NFT. You keep it as an NFT. That's your product, right? And you secure it with your private key. Now, if somebody gets hold of your private key, all those your stuff belongs to another person, right? So, and that's why most you don't even see the private key. Even in the wallets, right? You don't see your private key, really. It's when you are trying to make that transfer. Remember that the SendB wallet, if you say send, for example, it will ask you for the receiver's public key. You put it. So it creates a script. The script has to do with whatever you are trying to do. Whatever both of you agree will be created into a script, right? And that script will be hashed, okay? And now you sign it with once you sign it with your own private key, it becomes an authority, it's there on the blockchain. The sender, the receiver, once he just logs on with his wallet will unlock, because only his own public key, right, can unlock, only his own private key can unlock whatever you did. And let me say this, your public key is generated from your private key. So first of all, there's a private key. From the private key, there are some hashing mechanism that goes through, blah, blah, blah. Then you get a public key. Now, the thing is, you cannot go from public key and guess what the private key is. Not possible. So seeing a public key cannot tell you what that person's private key is. A one-way thing. So from your private key, you generate your public key, all right? Now, by that your public key, only your private key can unlock whatever it is. So when a transaction is done, and you are supposed to be the recipient. So only once you log in with your private key, you can unlock it. The script, your private key will unlock whatever script it is. If you match it, and boom, you own that thing. It still lives in the blockchain, but you own it, and only you can transfer it to another person. No other person can do that. Okay. So keys can be generated and managed by users' wallet software without reference to the blockchain or access to the internet, yes? And the public key is used to receive funds, and the private key is used to sign transaction to spend the fund. Now, Bitcoin addresses can be generated from your public key. So that your public key actually will use it to generate your Bitcoin address. I think I have, okay, not your public key, addresses. You can have a script that's an address, right? You can have a script. I can make a script that, does certain things. You encode all the condition in that script. So that script will have its own address. So you can make address from public key. You can also make them from scripts. In the script now, it doesn't go to a person's particular. It's that script that owns whatever that script runs. Whatever is in it will run and go as it's supposed to go. So, for example, here is the public key generation. I'm supposed to say address generation here. So I'll edit this. You can generate your address from public key. That's a mistake here. This should be address generation from public key. But the diagram explains this anyway. So we have a public key. We want to convert it to a Bitcoin address, for example. So this is your public key here. It goes through a hashing method. We'll see this hash in a bit. We'll actually go and test it out. It's part of the hands-on we'll do. So you have your public key, it goes through the hash, which is the SHA-256 in this case. It's a double hash, right? There's another hash again, the read med 160. Does whatever it has to do. Now produce your public key hash here. And again, these are some long numbers that you want to encode it. You want to do certain things with it. I'll give you an example. If you make an address where you have 0, you have O, sometimes 0 and O can be confused. I, L, small l, and I can be confused, also, and capital I can be confused. So sometimes this encoding, they take care of that. They rip out all those common words like 0 and O, for example, so they rip off all those things that can confuse someone, make it as more human readable as possible. That's the whole point of this encoding. You have the base 64. You also have the base 58. I think the base 58 finally does the encoding, and you have what we call your address. And again, during the encoding, it determines, it tells, for example, if this address is for a public key for Bitcoin, start with 1, right? If it's for a script, it starts with 3. So when we will study that index, you will see how they are the naming convention. How when you look at an address, you should know, okay, this is so address. Oh, this is secret address. This is that. You will know just by looking at it. So all this mechanism goes into your public key and gives you your address. This is address you now give to someone. Example, the BSV, your BSV address. If you want to receive BSV from somebody, you're going to send them your BSV address, right? That BSV address has to do with your public key. You can see that already. So when that person now forms a script, it's not that person that will write any script. No, you don't write a script. Once you say pay, it happens in between. We will do the scripting. Part of the course, towards the end, we're looking at scripting. So you see how the scripting is done. You can do, and it's in the scripting you can do a lot of things. You can set up something that says 6 months after so thing has happened, send this asset to this person. It will share. Whenever it's 6 months, it will happen automatically. It takes a life of its own. You can execute a contract that says, whenever this thing happens, do the other thing to other person, right? You can use Oracle to know when that thing happens. Once it happens, it will do the other one. That's the whole point. That's the beauty of it. So you're a lawyer, you could leverage on smart contract. I think that's the way to go in the future. You use smart contract to execute your contracts. So you don't need, and there won't be need for an arbitration or anything, because once the conditions are met, the script will execute and you get whatever you're supposed to get. So that's how you generate your address, which is the basis of what you do. Now, transactions are recorded on a public ledger. Transactions that are recorded on a public ledger are visible to all parties without the need for a financial institution involvement. Remember, if you do a transaction, like we said before, involving banks, yeah, I mean, you only you say, okay, you've done this. You don't know what's going on in the other person's account in his own bank. You first have to go to your bank. Your bank have to now speak with the other bank. They have channels for doing that, and they'll sort things out. But in a Bitcoin blockchain, everything is public. There's nothing hidden. So let's go take a look at Bitcoin blockchain. Let's see what's going on there right now. I did this screenshot today. What time was that? You can see January 3rd, 2023 by 10:41. That's when I actually prepared this slide. So I did this screenshot at that point. And when I did this screenshot, I could see a hash here, some numbers, it's a long number here, and 1.4 Bitcoin. This person made a transaction of 1.4 Bitcoin today, which was worth about 23,500 USD, And it can be so small too, like this other one, just about $5.25. 0.0003 transaction was made. This was made 10:41:52, almost the same time. All these are 52 seconds, almost the same time. They all happened at the same time, right? And you have this other one here. So let's go live and take a look what's going on right now in the blockchain, in the Bitcoin blockchain, rather. So I'll go to my browser. I'm using Google Chrome here. And And in my browser here, we go to, let me just Google Bitcoin Explorer. Bitcoin Explorer, okay. Okay. Yeah, I can click this one. Let's take this. Um, 1 minute. My other connection is slow. I'm sorry. Okay, I think I have one of these. Okay, here we go. I think we are fine now. So here, let's go to latest transaction and see what's going on. So I'll click, this is the Bitcoin Explorer, just blockchain.com/explorer. Okay, it's explore both the blockchain and Ethereum and different block. Yeah, so we go to latest transactions here. Let's take a look. Take your time. You show up in a bit though. Okay. While that is trying to load, I could just say I'll be too tiny for you, the screen now. All right. Let me see. I have one open earlier on. Let me see if I still have that tab up. Okay, I have a Bitcoin something here. Let me see. This one. Maybe I should just, my power has been restored. Maybe I should just change back to the fiber optics connection. Okay, here we go. No needs. Okay, see what's going on here. Let me pull this out of the way. And that one out of the way. Okay, see, transaction is coming in real time. So you see, you could see it just moving, literally, right? So this will happen real time. We can see what's going on. Like, I can grab one. Let's take up one of these. Let me click this one. This one looks interesting. Let me click this. Where is it again? Oh. I'm not sure if it clicked. Anyway, so you could see real time what's going on. It's a public blockchain. All we are seeing are addresses. This address, for example, the about 1,000 Bitcoin.USD, rather, worth of, since it's loading. So you could see them happening real time. It's a public blockchain. So if you tell me right now, if next we are supposed to pay me, sorry, you are supposed to send asset to someone. I say, hey, I transferred this asset already to you. No problem. Can I have the hash? Because if you transferred it, you will have the hash function for that. Just give me the hash, okay? If you give the person the hash, if the person gives you the hash, rather, you can come here, click in the hash somewhere, do search for it. It's either it's there or it's not there. You see, so when we use blockchain for micropayments, it's better. You know, it guarantees certain things. For example, it guarantees that when a transaction is done, it's actually done. In a normal traditional system, yet you could make a transaction to some. In fact, I've seen that before. I've personally made a payment to someone, right? And it left my account. I could see it go. I snapped the screenshot and sent to the person. It's gone. Then was it 2 days after I was doing something? I looked and I saw, oh, the money came back to my account, right? So I needed to get back to that person. Hey, see what happened. Also, even with POS, I think one day I was traveling from Onitsha to Warri or so, yeah. So I had to use public transport after I got through a motors, yeah. So the guy in the ticket seller also does POS. So I paid him with POS. No, I took some cash from him, and from there I paid him. He took it from my POS. I now went. Returned later, 2 days after I returned, I noticed that transaction came back to my account. So I had to go back to the package and say, hey, that stuff you did, it didn't return. He said, oh, thank you, thank you. And he don't even know who I am, because that was a public pack, but I know him. And because I know where I did it, I had to go back and say, hey, so do it again. Here's your money. He did it second time and took back his money. So you have all these problems. But for a blockchain, for example, once your payment is made, it's not coming back. So it brings closure. Now, with micropayments, now you have to people that are unbanked, and you develop an application that could be able to, connect farmers with their buyers, right? And maybe, of course, finally go back into, because I know the whole cryptocurrency issue with the regulation right now won't be forever, right? At some point, they'll have more control of what's going on, and it will open up more use cases for the e-naira, integrating with other forms of payment. And this is what I think will happen over time. So I pulled up one of them. Here is it. You could see it came from this person. This address here is just a short form. BC1Q, there's a hyphen, blah, blah, blah. I can copy it and paste somewhere, right? And you have the script. I mentioned about script. Script is actually what gets transacted. So when you want to make a transaction, for example, this is the script. We'll explain what witness is later on in the courses, okay? But this is the script, and this is an opcode. The opcode here is 0. You will know what all this means as we go on in this course. So let me say this. So when you send transaction on the blockchain, what actually matters is the byte you're sending. It doesn't know whether you're sending 2 million worth of naira or 10 million worth of naira. So someone sending 10 million worth of naira doesn't make sense. So it doesn't make much difference to the network from someone sending only 1,000 naira. Because what actually gets sent is the bytes, the script goes. So how long your byte is, how long the script is, determines how much you pay. It determines, what they're gonna charge for that. So you can actually send 20 million to someone with maybe 300, maybe 100 naira fee. Yes, 100 naira fee, you send a whole 20 million goes, right? So the problem now for someone that wants to buy bread is about 1,000 naira, 1,200 will buy you a bread. So if you're buying a bread, for example, in the BSV, that's why BSV we shows work with BSV. In BSV, the fee is upon zeros is so low that you could buy a bread and your transactions fee could be 50 naira, for example, just 50 naira, right? Very, very low, just so low, okay? Unlike some other blockchain where you're trying to make a transaction of, say, 2,000 naira, and your fees are above 2,000 naira already. So that kind of thing does not support microtransaction, okay? Yeah, it doesn't support it. So do I see the fee for this thing? Let me take a look at this. Yeah, it has 2 outputs. It went there and went there. We understand when we start doing UTXOs, how you combine your inputs, right? And get your output, how many outputs you have. So what matters is the byte. So the smaller the input you're putting, right? The lower the payload for that. So it doesn't really know what you can send a billion with the same charge of somebody that sent just 1,000 naira, you pay the same charge, basically. So yeah, back to my slides. Okay, so we say it's a public ledger and visible to all parties without the need for finance. We've seen it now. We've gone there. Only thing, we don't know who owns that address, right? But assuming it's an address you're interested, you already know the address, so you can put it there. And so I've been involved recently in a case where some people have issue, they say, oh, I paid you so that the person used his phone and transfer so stuff. I say, well, no problem, it doesn't matter. it's in the blockchain, we'll go and see. So I just grab only one of the address, right? I go in there, for that address, I put all transactions that have ever happened to that address, and we could see it. And also you can also triangulate, you can actually trace, triangulate it, trace every other address that have gone to. So it's easy. Auditing, for auditing, is like, not, you can run your audit without an auditor, basically, because you can write simple scripts that you give in one particular distance, we form the whole trail about it, give you the audit report. And it's, that audit report is, anybody can validate it, you can verify it. You don't require rocket science to verify it. So the blockchain has lots of promise, especially like in area of auditing now. If government bring in blockchain to drive almost a transaction going on blockchain, there will not be waste anymore. I mean, you will see everything that happened. And everything that happened, yeah, you could see it. Although government mainly, you don't expect them to go, they usually go on their private blockchain. You have different types of blockchain. You have the public blockchain, like now, the Bitcoin we're talking about. You have the consortium. Consortium banks will come together and say, hey, let's form a blockchain for the purpose of utilizing the benefits of blockchain, but it's not open to the public. It's only by invitation. So maybe you have to be a bank or someone in the financial, to be able to invite it on that. So that's a consortium. And then you have the private, right? Or like the CBN will have its own private blockchain, we used to run consortium. I think they did a consortium on the CBN stuff, where you used to run, and the only thing is that it gives you control, full control. So you can decide to make any change. If CBN wakes up tomorrow and say, you know what, for the e-Naira, we want this to happen, they can implement it like this on the go, and it will start happening. That's it. But for a Bitcoin blockchain, the protocols are there, they're all set, right? For you to make any change, it's a long process. It's a long process. People have to vote, miners have to vote, developers have to vote. It has to reach certain threshold, before finally getting come. So there are many improvements that have been proposed, but they haven't been implemented because of, and of course, that's how I should say public, nobody is in charge. Remember, it's decentralized. The math have been done, the protocol have been done, but there are what we call improvements that happen with them on them over time. All right. Sorry, I'll get back to present. Why was I off from present in the first place? Yeah, my internet right now is not so great. Okay, so we've seen that it's public, anybody can see and verify. And yeah, so that's what we call the digital signature and trusted third party. So digital signature provide part of the solution, but the main benefits are lost if a trusted third party is required to prevent double spending. So look at the image there. You see two people trying to transact. The banking institution off completely. When you remove it, it's just the two people. All you have to do is to sign a transaction. I told you before, to sign a transaction means your private key. And it's not like you do anything manual. When you are saying pay, when you're trying to send anything to someone and you click to go or send, the script runs. It puts all the keys, all those. Let's say if you say, okay, send 0.0 something to Mr. B. So that 0.0 something is part of the script, right? Mr. B's public address is part of the script, right? The conditions, if there are conditions you want to happen, you could have a situation where for corporate entities, for example, you don't expect only one person to be able to approve something. In a normal setting, a corporate organization, 2 people will sign or 3 people will sign. They might say, we have 5 signatories rather. Out of that 5, 2 must sign for a transaction. So you have 5, yes. Any of those 2 must sign. You could say Mr. A must sign, then any other person. There are different. You can also do that in the Bitcoin blockchain. You could have multi-signature, we call it the multi-sig, and you could state condition. You say, okay, you have 5 signatures. Out of that 5, 3 must sign for so to happen. When you start your group work, your project work, for example, it should be a project thing. When you want to deploy on the blockchain, you can't use one person's address, for example. So out of the group, 3 people might become, it may depend on how you want to work. You might have 5 people say, hey, 5 of us, we are the key guys here, all right? So we all of us have to sign for this to happen, or 3 out of 5 of us must sign for this to happen. So before you do anything gets, executed, let's say you want to deploy finally, or whatever address supposed to hold all your assets, right? So you have those signatures. So 1, 2, 3, we keep checking 1, 2. If you say 3 out of 5, once the third person does it, it executes. So all these things goes into a script. You don't have to, once you state all those conditions, they go into a script. And when you say execute, it takes all those things are running. So these two signatures, they provide part of the solution, but the main benefits are lost if a trusted party is still required to prevent double spending. So what is double spending? It's a recurring theme in blockchain, double spending. Okay. Where am I at? 1 minute. I think I've seen this before. Digital signature are the means of the owner of a coin to ledger, yeah. Okay, I think I've not seen. So we're talking about signature. We'll come to double spend in a bit. So these two signatures are a means for the owner of a coin on the ledger to establish their intent to use that coin in a transaction. So these two signatures, they work by generating a unique hash of the message and signing it using the sender's private key. The hash generated is unique to the message, and changing any part of the message will completely change the hash, thus rendering the digital signature invalid. So whatever you do is being hashed. Let me show you this. Let's see something about this hashing system in the SHA-256. I think I have this file open. Let me check. No, that's in my Firefox, I think. Yeah. Okay. So let's take a look at a simple thing, how this hashing thing does. It will help us when we're looking at the proof of work to understand more how the whole works. So we've seen SHA-256 before. It's a hashing mechanism. What it does is to, let me say, welcome to introduction to Bitcoin theory, part 1. Now, I wrote out something, all right? Now, this thing I wrote is being hashed using SHA-256, and it generated a unique key. Look at it, the hash. It starts from 10, blah, blah, blah. It enters 060. Now, if you change any part of this, it will change the hash. So we are saying when transactions are being, you say, you give all the condition and everything, and it's all being hashed, you generate a unique key, right? So let's say if I say part 2, let's see what will happen to these numbers here. Let me just change 1 to 2, and we'll see. It has changed. It's no more that. But if I put it back to 1, it gives me the same exact key. So when you hash something, it doesn't matter the size or anything. It just gives you this 4-bit character here. It compresses everything just into this. When you download certain software, for example, from a vendor, they will provide a hash. Where did we see that? When we are trying to install, is it that Golang? One of the software one of our courses, I think it's in Golang or so, where you have different versions, right? I can't remember. Maybe either Golang or VS Code, one of them. I know when we wanted to download it, we saw a key, a hash associated with each version. So what happens is when you download the software, you use your own program, your machine to hash it. If you hash it, if it gives you the exact same hash, you know that it's genuine, because the owner of the software say, hey, this is my software and this is the hash of the software. Okay, just go with it. Now, if you do a hash of that software, it doesn't correspond to what the owner gave you, that it has been tampered with, maybe maliciously, or it has been improved. Not necessarily maliciously, it has been improved, right? So something like that could have happened. So this is it. If you change this to, if I remove 1 entirely, it changes also. So whenever you do a hash, it gives you this unique key. The thing about hashing is that from this unique, you cannot guess what this is. But if you're able to guess this, there's no point of hashing anymore. All you see is this key. You can't guess. But if you give me a hash, right, and what it is, I can verify. So let's say this is part one, right? Part one. So let's say it stopped with 060. It started with 10, stopped with 060. So let's say you tell me, hey, this is a hash of a message I sent to you. I said, okay. Okay, give me the message. Let me confirm if it's correct. If you give me that message, I can know whether the message is correct or has been tampered with. So if I know the message, I can verify. Let me paste the message here. Paste the message. It started with 1060. So to generate the hash is a complex thing, but to verify is very easy. So you can verify just one single boom, you are verified. We'll see how that is implemented during the proof of work. To generate the proof of work is very difficult. But once you find the solution to proof of work, any miner can verify it. Boom, you are verified. So that's the beauty of it. All right. Back in my presentation here. So the hash generated is unique to the message, and changing any part of the message will completely change the hash, thus rendering the listening signature invalid. Yeah. One minute, one of NITDA present button. Okay. Okay, why that's loading? Been here. Okay, so we've just seen this already. In this case, I said Satoshi Nakamoto, and this is a hash for that. So each time you type this, I remember this capital S is different from small s, but if you type this exact word with a space in between them, you always get this hash. So to verify is easy. The problem is to generate it, and it's a one-way thing. You cannot go back the other way. Okay, so a transaction consists of a condition under which a coin can be spent. You know, that's what a transaction consists of. Now, Bitcoin uses the elliptic curve digital signature algorithm, ESDSA, to incorporate keys into a transaction script. Now, miners, their job is to validate and record the transaction. That's their work. So when you have a transaction, I just showed you, you can validation is simple. So once you have formed that transaction script already, you form the transaction, right? A miner can validate it. To check it is easy, as we just saw, because you already have generated that. So we will just say, oh, is correct, right? They don't know what the contexts are. They don't know whether you are sending 1 million USD or 2 million Naira or, Naira. They don't know whether you're sending 500 million Naira to someone. They don't know. All they know is that it's valid. They could verify. And once that happens, they record it in the transaction. So some way, you could say, yeah, they get paid for their fees. That's what we call the mining fee. When you are making a transaction, let's say you want to send 5,000 Naira to Mr. B, okay? Now, normally you might send 5,002 Naira or 5,005 Naira, something like that, or 5,050 Naira, okay? So that difference, that 50 Naira difference is your fee, is the fee that the miner will take. And the miner will see it, he will know. Like, remember when we went to the Bitcoin blockchain, transaction was just roping in, boom, they were coming in like in seconds. In a second, we have so many of them coming in. So we have what we call the mem pool. All transactions are there in the memory pool. Miner will now come and say, hey, you know what? Let me check. I want to record some of this transaction in the blockchain. We'll get to blockchain in a bit. But if I want to record some of this transaction, you now come and look. Oh, this guy wants to pay me 100 Naira. Okay, let me take it. This guy is paying 50. This guy is paying 80 Naira. So miner will choose the transaction he wants to record. He's not bound. He's not bound on any, it's not bound by any law. People that have more fees, So if you want to still send something at a very low fee, you just have to have patience. You have to wait. Maybe you create your transaction when it's not very busy, like there are ways to check. There are ways you could find out the countries that are quite busy. And those countries, during their working hours, just know that, yes, it's very busy, okay? You wait when the network is not too busy. You can also look at the graph and see when they are low, right? So if you do that time, you could make your transaction for a very, very low fee, almost to zero fee. You can make that. The miner will still pick it and put, right? So what I'm trying to say are miners, yes, they validate and record the transaction, but they're not a trusted third party. In banks, in central bank, they'll build the role of trusted third party. In this case, these guys are not trusted third party. They're just a simple third party. All they do is to validate the transaction and record it, because they have the hardware, they have the Bitcoin nodes they are running. Some have the farms, okay, the rigs, the mining rigs, called the mining rigs, all right. So they spend a lot of money in energy in maintaining those rigs. So they get back, and for every block, they will see that later on. For every block you mine, you have what called the Coinbase. You are paid, you are given an incentive. For every block you mine, you get something. We will see that later on, not in this course. So it forms the Coinbase. And then on top of that Coinbase, they'll now add more transactions, depending on the number of transactions that the block can have, 2,000 plus transaction, whatever. After adding them, then they start, we'll say that in a bit, trying to do what we call the mining. Yeah. So peer-to-peer network. So we propose a solution to double spending problem using the peer-to-peer network. Yeah, that's double spending. So what is double spending exactly? So double spending refers to the act of signing a coin to create a transaction and submitting that transaction to the network before using the same transaction to create a different transaction, which pays to a different recipient. So peer-to-peer network of nodes gather and validate transaction, validate and timestamp all transactions that takes place. So let's see. So double spend is a case where you want to pay Mr. A, let's say 5,000 naira, right? So you bring your UTA, your unspent transaction output. That's worth 5,000. You could join 2 or 3 or whatever, how many there are. You join them and they create 2 transactions. One that will pay the exact fee, one that comes back to you. And the difference in the 2 of them will be what goes to the miner, all right? So you send this out and you say you're paying Mr. A. I have a diagram moving. Let me go back to that diagram. 1 minute here. Not this, probably. Okay, never mind. So what happens here? Once you pay Mr. A, and you go back, maybe you could do the scripting. You take that same transaction, unspent transaction you used to go, maybe why it's still out there to hit Mr. A. You use it also and pay to Mr. B. So let's say you use a output that is, let's say 2,000 naira worth. You combine with other ones that are okay, right? You pay this guy. You still want to use part of that 2,000 naira you already pay to that guy, that UTSO, to pay another person. That we call double spend. Now, if you can do double spend on the blockchain, then it's useless. Useless. There's no point for having a blockchain if you can use the same UTXO 2 times, right? Like, there's no need. So the whole point is it prevents double spend. And how does it do that? So you can't spend, whenever you spend any UTXO, it's marked as spent. We have the unspent and we have the spent UTXO. So whenever you use any one, it becomes spent, right? And once it's marked as spent, you cannot use it on the network. So part of validation that miners do is to know this transaction, is it valid? When we say is it valid, does it have any spent UTXO on it? If it does, it's invalid. And how does he know? Because there's a maker tree. I think I will have that in the next slide, where we'll talk about the block structure. You see how for every transaction that happens, it's stored in the blockchain, and it's stored in what we call the Merkle tree. In data structure, Merkle tree is one efficient way. Use what we call the binary trees. is one of the efficient way of storing data, where you don't have to search through all the records. If you know what you're looking for, they say you could actually go just get to the record, minimizing so many other records. Let's say it's binary. So at each base, you have 2 each base. So if you want to go, let's say I know that this is less than 5. I go to where 5 is. You know that if it's less than 5, you go to your left. If it's more than 5, you go to your right. So if it's less than 5, you don't have to go to your right. So everything in the right, let's say a transaction have 5,000 transactions. So everything in the right of it, since it's a perfect binary to everything in the right of it. So 2,500 transactions is off. You are not searching them. You come to this place. If you come to that one again, also, you check the number. If it's less than this, so at each point, you share the problem into half, remove the other half. It's quite fast. It's a very efficient way of writing programs, to be very fast using the Merkle tree. That's why we're going to study Merkle tree as a course along this. So it will check, and if you have spent that before, if they have, remember what we say, there's a timestamp for every transaction that comes. There's a timestamp on it. So if it sees 2 transactions with the same stuff, it will take the one that has the first one, because there's a timestamp showing, okay, this one has been seen first. That's what this paragraph here is saying. It accepts only the first seen transaction that spends a UTXO, right? Now, each transaction can only be processed once. And input they will be consumed, means you can't use them anymore. So why is this? Peer-to-peer. So whenever a block sees any transaction, it broadcasts it immediately to the whole node. So let's say you are the one now, you have your wallet. So you started it from your wallet, right? And your wallet did the transaction through whichever node that is closest to it. So a block happens every 10 minutes, yeah? But that's forming a block. But transaction itself, we saw when we went to the blockchain explorer, we saw transaction dropping like this. So for each one that drops, it's being broadcasting automatically to every node in the network. They will know that, oh, this transaction has happened before, right? So it prevents double spending. And because it prevents double spending, you're guaranteed. So when we say, for example, you have so finite number of digital assets, you know that that's what it is. And you can't have a double spend on it. Okay. So yeah, okay, here is that timestamp. Yeah, that's what we're looking for before. So the network timestamps transaction by hashing them into an ongoing chain of hash-based proof of work, forming a record that cannot be chained without redoing the proof of work. So see the blocks that come, the transaction, not blocks, transaction. Each one that comes, it has a timestamp. You see that? Each one that comes, it has a timestamp, right? And yeah, it forms block. And then each transaction is chained together, and it's very long stuff. For you to be able to undo anything, you have to undo the whole proof of work. And we'll see how near to impossible that is to happen. Okay, time chain and proof of work. So as transactions are received into the network, nodes capture and collate them into logs. They go into logs, right? These logs or blocks are made up of timestamps applied to a sequential list of transactions. So the miner picks any transaction he wants to pick and put them in the block. What happens is that every miner starts, once a block starts from another forming, let's say we form block number 10, just for, I know we're in thousands now, just for simplicity purpose, we have block number 10. Once it's formed, boom, everyone will start working on block number 11. So all the miners will start gathering transactions. Once they hit all the transactions and everything, they start mining. We'll see that in a bit, right? So whoever solved the problem first, hey, that person is given the right to form a block. Other people that whatever you had before, you put it back into the pool. So let's say you have collected somebody's transaction before, you wanted to mine it. Another person mined before you. That transaction your own probably is not part of the one that person mined, okay? So whatever the difference is put back into the pool. Now, in the next batch, they'll start grabbing again. So that's why sometimes you want your transaction to get into faster you put a more attractive field, miners will tick it immediately and it will go in faster into it. So it represents a consensus agreement of the proof of existence and validity of all transactions they contain. So for you to build on any block means you have agreed that everything in that block was correct. Because we'll see in the next phase how for any block, you have a reference to the block before in the previous block, right? So when you are building on a block, you are extending the proof of work. You are saying yes. So when you have a transaction that is 6 blocks away, nothing can change that transaction, nothing. I said nothing in the sense that, think about this. You have thousands of miners doing the mining, right? So let's say they're mining for block number 11. It's possible that 2 miners will mine that block the same time. It's possible, yes? So when they mine the same time, they broadcast. This A will broadcast to the nodes around him. Maybe B is another location broadcast. So the nodes around A picks A on and are extended based on A. The nodes around B picks B and are extended B. So we have like a fork. You have this one, A transaction A going in one segment, transaction B going to that segment. At your point, they will not meet. So who takes over? Who becomes the real one? The thing is that before you could even think Jack, another person have done a new block and will extend one of them. So at the end of the day, whoever got extended more becomes the correct block. So you have mined, this guy have mined, but this guy's own got extended by other people before yours. You have longer chain this guy, so they have to drop your own because they won't take the longest chain. The longest chain means it's a better, a better indication of, how solid the transaction are. Yes, the longer the means we have more proof of work than the one that is shorter. So for that one that have mined before and it didn't got built on, it will be dropped. So all the transaction into it, of course, go back. Even the reward I got, everything goes back. So it doesn't go through. So at the end of the day, you have only one chain being elongated. So here, so proof of work. I was trying to a way to explain this. I just think the best way is just to explain certain terminology. After I explain the terminology, you will now understand what proof of work means. So in a typical block header, this is what you have. In a typical block header, there are some fields that are mandatory. So remember, a block is just list of transactions. You have put transactions together. So at a start, okay, let's follow it from the beginning. So you are a miner, right? And you want to mine something. So first of all, of course, each you have your protocol number, your version number, because there are different versions of Bitcoin protocol going on. So wherever we are now, you have a different version number. So you put the version, of course, then you make a reference to the previous hash. Now, let's say we are trying to mine block number 11. So you take the hash of block number 10 and put, because you have to show what is the previous. Remember, I say shared, you have to refer the hash before your own. So you put that, and then you go to the maker root, make a hash of the maker tree of this block transaction. Do everything, you make a hash, all right? Then you have the timestamp. Is the creation time for the block. It's in second, I think start from 1st of January, 1970. So when you see time in blockchain, you see thousands of seconds. Just know that it started from 1st of January, 1970. So you could do the math and know what time it is actually. Okay. And now we have what we call the target. The target is the proof of work algorithm target for this block. Now let me explain this. For when we say you solve the problem, so I keep using that word. When you now solve it, what problem are you solving? They give you a target. They say, hey, we want you to solve this mathematical problem. In this mathematical problem, we want you to form a number that is equal to or less than, let's say this, right? Let me open up my any text editor and type out something. Maybe it will help us get more. So here, here's my code editor. Okay. So let's say I have a number 0, 1, 2, 3, 4. Oh, no, let's take this. Let's say we have 2 dice. Yeah. I have 2 dice. And I told you, throw those 2 dice and give me a number that's equal to or less than 11. And this. Okay, we have 2 dice, and we want a number that is less than or equal to 11. So, you know, the sample space for this will be 12. You know, we have 6. The highest you can get in one dice is 6. The highest you can get in the other dice is 6. So if you throw the 2 of them, the highest you can get is 12. Let's say you got 6 here, 6 here. So if I say I want number less than 11, so it means, you know, the sample size, I think 23 out of the possible 12. Okay, yeah, you can get 11. So let's say I come again, I say, you know what, give me a number that is less than or equal to 7. Now think about this. It will be a bit more difficult for you, because what that means, in this case, I will not accept 8, 9, 10, 11, 12. They're off. You only have 7 to deal with. So, and you know, when you throw your die, by probability, you can get 11, you can get 12. But when I say 7, your chances are limited. Think about it. Before I said, give me a number less than or equal to 11. It's easy for you, because you could throw it and get 1. It's valid. 2 is valid. 3 is valid. 4. 11 is valid. So it's easy. But when I say give me a number less than or equal to 7, it becomes a little bit difficult, in the sense that when 8 is off, 9 is off, you don't need them. Then what about if I now say I need a number that is less than or equal to, let's say 6? Now it's more difficult, because half of the numbers you get will be invalid. So it will take you more time to get this. And now when I say give me a number less than or equal to 2, for example, it becomes more difficult. It's only when you have 1 on both of them. So you see, you have to throw so many times for you to be able to accept this. So what happens in that math is that they will say, give me a number that starts with 0, 0, 0, 0, 0. No, let's take this. 0, 1, 2, 3, 4, 5, 6. Just let the first number be 0. It's easy. It's not so difficult. You can try and get 1, 0. But when I say give me a number that is 0, 0, let's look at that. To make this more lively, let me get back to that equation and see. No, that other here. Okay, let's say we want a number that starts, this one starts with 1, but I want a number that starts with 1, 0. So let's say I have 1, 2, 3. If I keep that, let me remove this. You see, I typed 3, I tried 1, 2, 3, 4 times, and I got a number that started with 0. It wasn't difficult. I just did 4 tries and see what we got. But if we want numbers that start with 2 zeros, we're reducing our sample space now. I want a number that starts with 2 zeros. So let's see if we can get to, we have 1 0 already. Let's press another one. 5. Oh, it's even gone. Let's go. Let's keep going. I'm typing. See how difficult, I'm not even getting a 0. I'm just trying to get 2 zeros. That's starting with 2 zeros. It's now difficult for me. So when you add more zeros here, it becomes more difficult. But there's a way to solve it. Let's look at that diagram we saw again. Let me put it back here. There. I won't escape this again, so I don't have to present each time I come back. Okay. So here, that's where I'm talking about target. So target is they give you a target. That target is a proof of work. They say, find a number that is equal to or less than so stuff, and it starts with 0. So it's difficult to get number that start with, let's say 0, 0, 0, 0. You know, the more zeros that I start with, like I showed you already, as you are decreasing your sample space, it's becoming more difficult. We saw with the dice, trying to get dice, right? So what's here? We want to find, this is a target. We are giving a target. Now hash everything that is here. Hash me all this stuff. And let that hash has a number that is equal to or less than this target. And this target starts with 0, 0, 0, 0. Now, all you have to do as a miner is here what we call nouns, number used words. You first of all, you initialize this to 0 before you start as a miner. So what your mine, you know your target, all right? You do your hash, right? Then you now start changing this number called nouns, incrementing one at a time, so that you'll be able to get a number, so that you'll be able to get a hash value that is equal to or less than your target. So let me go back to that program here. We have block there. Let me get to block. Now take a look at this. Okay, so here we have block 1. I have nouns. Now look at the hash. This hash starts with 1, 2, 3, 4. 4 zeros, yeah? 4 zeros. Now this is empty. There's no data here. And this is, if you have an empty block, nothing inside it, and you have this block header 1, if I hash everything with this empty, I need this particular number here, 72608, for me able to have 1, 2, 3, 4 zeros. Let me change something here. Let's say if I remove 8 here, this 8 on nouns. See, I don't have 0 anymore. So for an empty data like this that have only those hash values, I need, what was it? Is it 8? Yes. So I need to keep increasing this number. You see, what 72,008 before. Now, what if you now have, okay, so in a real life, you've done your hash, okay? You want this to be 4 zeros. How can I make this 4 zeros? That's the work of a miner. Here you see mine. When I hit mine, what it will do, based on this number I just wrote out, let's say we started from 0. And I write all this number, okay? This is what I have here. So it will find me what number shall we have here to be able to turn this into 4 zeros. That's what mining is. So I have a target. Remember, our target is less than or equal to 4 zeros. So here I have, if I say mine, let's go. It's mining. It's trying to find the number. It hasn't found it. It's still mining. You see the time it's taking? Am I sure I'm going to even get something? Maybe my processor is too slow for this. But it's mining though. And I'll give you something simpler so we don't stay here forever. But you get the idea. Let me fast forward a bit. In the Bitcoin blockchain, it takes average of 10 minutes to mine a block. And why do we say it takes 10 minutes? Because they made the difficulty to the point that before you can get it, it takes you 10 minutes before you can get the solution. Now, if you're using an ordinary machine like normal processor, it's difficult. You might not even get, right? Well, oops, I can't even stop this. I hope it's not a bug I have. Yeah. Anyway, so it's taking it forever to mine. If it were a simpler thing for it, it should mine it and you give me something called here now. So see what I'm trying to explain. Now, see, I mean, it got it. It has mined. But see all the time it took to be able to mine this block. What did we get? 1568448. That's the nouns. The number that once you get this, it will now give me how many zeros here? See, 1, 2, 3, 4. 4 zeros. So if I increase, though I can, this program is set by default to just do 4 zeros. So if you add more zeros, it becomes tougher, right? So with all these things I have here, you need this now to be able to mine this block. It's green now, means this block has been mined, all right? So let's get back to the diagram, so the presentation rather. So we've explained what the target is. The target is they give you a target. We want 7 zeros. We want 4 zeros. Okay. So your work now is keep incrementing your nouns until you get a hash value that starts with 40. Now, when you're able to do that and you get that nouns is your proof of work. Now, think about this here. For example, let me come back here. think about this. This guy has solved the problem. You need this nonce here. So if I'm a miner, I want to, if you want to verify your proof of work, you have given all this nonce here. This is your proof. Let me copy this, but I might not know I'll copy C, Control C. I copy the whole number here. So me as a miner, I have all this already. What I'm going to do, I just go, okay, this is your nonce. Let me put it here. Control V. Correct. You see what we are saying? It took you a lot of time, up to 10 minutes, for example, to find a block, to mine it. But verification is very simple because you already have, we know what your nonce is. We know the difficulty level. You will see it and you know what the nonce is. So finding out, verifying is so easy. So that's what miners do. For every thing, they will verify. When a new block comes, they will verify the block. Is it correct? Remember, block has all these things. A block, we have the, where are we at? A block, we have, yeah, the maker rule, the timestamp, the target, the nonce. So you just check it. Verification is very, very simple once you have solved it. So when we say, what is your proof of work? That's the proof that you've done the work. Because if you've not done the work, you never get that nonce. So when you have got it, that's a proof of work. And the proof of work, the difficulty level varies. If, for example, people start getting, as people are, imagine when Satoshi Nakamoto started, it's very easy. You can even use a toy phone to mine. It comes out easily. But as it's becoming more sophisticated, they are building machine. Right now, you need ASIC. They now use ASIC processors, you know, to be able to mine faster. If you're using the normal regular one, you just keep running and running and nothing happens. So except you join a consortium, you know, join a team where they man, you know, they form a group and everybody bring their resources together. So when they get it, they share it according to your contribution to that. Other than that, you will never get anything mined. So that's what happens in a typical blockchain header. When we say proof of work, we want a proof that you actually did that work, all right? And it's in that, you look at that, you can verify, yes, this work was actually. So that's how that way will verify. Oh, okay, I was almost there, but yeah, you got it first. You that get it, you now have the right to form a new block. And forming a new block means once you form that block, you'll be paid what we call the Coinbase. About 16 point, it was 50 USD when Satoshi started it. Every 4 years we keep halving, right? And it will keep continue until maybe everything it tends to zero. At that point, miners will be paid by transaction, means transaction will not go up. So that's why in something like the blockchain, for example, is the opposite of inflation. Rather than have inflation, have deflation because it's fixed, right? We know how many it is. It cannot go beyond it. So at some point, people will start holding it because it becomes more valuable and people hold them. So when we say proof of work, you want to show, yes, that you actually did the work to mine this. And we see that in the header, in your block, you put it in the header, other people can verify it, yeah? So the miner calculates the hash of his block header and sees if it is equal to or smaller than the current target. Now, if the hash is greater than the target, the miner will modify the nonce. It's usually done, okay, yeah, increment it, you keep trying. I've seen that already. So miners have to try quadrillion times before finding a nonce that result in a low enough block header hash. Quadrillion times. So that's why there's so much investment now in doing that and consume lots of power, you know, to be able to do that. So that's what we mean by when we say proof of work. You have to show that you actually got it. Now, for each block, you know, that is mine, you can imagine the work that went into it. So by the time you have 6 blocks, so for you to undo anything, imagine what it will take, the energy, you know, the amount of work it will take to undo all those stuff, right? All right. Okay. I have one algorithm in this. Let's just run it. I might have to call it quit here. I have one Python script here that will show, it will try to, yeah, here's the script. I'm looking at it already. So what it actually does is to what it actually does is to show proof of work. It shows all the difficulty. So what we'll do, we'll start with 1 bit. When I say 1 bit, 1 0, 2 bit, 2 0, start with 2 0, 3 bit, start with 3 0. You know, keep incrementing like that. Let's see how it will. So basically, here, so it takes difficulty level. We are taking from 0 to 31 bits. I'm sure I'll stop it along that because 31 bits, it will take my whole day. Not whole day necessary, but it will take a while. But let's see how it goes. So we'll start from 0 bits, like know everything. Then we'll have 1 0, 2 0, that's 2 bits. No, 2 0 means 1 0 means 1 bit, 2 zeros means 2 bits. So we'll keep going like that until that, but we won't get anywhere close to 31 bits. So what it will do, it will search for the difficulty, right? It will start searching for, it will calculate the time as it's searching, it will be calculating the time until it found the nouns that will solve that problem. Once it gets the nouns, it will tell us, it will show us and we'll see it. So I'm just going to run this now. Let me increase this, please. Okay, clear. All right, so here I have Python proof of work.py. Okay, it's working now. Let's wait. So it's starting. Let's see what's going on. This is 0.0667 seconds. It's 2.8 seconds. Now it's increasing. Difficulty here is 16 bit. For 16 bit, it's on 16 bit now. It's starting. Before 16 bit, it did 15 bit. At 15 bit, it take you 2.8 seconds. Now difficulty here is 16 bit. It's still searching. Let's see. Okay, it got that. So for the 16 bit, yeah, 17 bit already. It took it 0 point. So it's random. You could see, you know, it could actually find it faster, or it can, you know, depending on that it's a random thing, right? And that's why sometimes, even if you have a processor that's not so powerful, it could just be that randomly you just boom hit the number, right? But it's very low and far apart. Okay, so it's a random thing because you could see at some point it found it faster than the one before, but not now. We're in 12.4 seconds, and this is for 20 bit. You could see for 20 bits 12.1 seconds already. Now it's for 21 bit 33 seconds. See, so as you vary the number and look at the hashing power increases, right? So as you vary the difficulty level, which is the number of bits, you're reducing the sample size. It takes more time to be able to find it. And once you find it, success, that's the nouns here. That's your proof. Yes. If you take all those things you hash, put that nouns there, it will give you the same thing, right? So for 23 bits, it took us 26 seconds, right? So you could see we are 23 bits now, but it keeps increasing. 26 seconds at this time, 23 bits. So imagine what you take before it will get to 30. Now, imagine what it takes for you to do quadrillion times, you know, to keep doing it. This is just a simplified version. It's not doing much because I'm just using the regular processor on this MacBook Pro, and it's doing like this. If you bring another machine that is even not as fast as this one, it will take more time than this one. So, and then if you bring ASIC machine, of course, it will be faster than this, right? So it's a trade, and we know that when they design, they know that computer hardware, you know, their processing power will increase, and that's why there's adjustment. That's why the average time to form a block is 10 minutes. So every 2004 blocks, they will check what is the average time. Assuming people are solving it lower than 10 minutes, it will adjust automatically. Nobody does that, it's automatic. It will adjust the difficulty to be higher. So it will take more time. Now, if it checks, you see that people are solving it in more than 10 minutes, in order to keep everything back, it will reduce it. So it increases and reduces. Nobody does that. It's automatic, it's there in the program already, and it does it automatically, right? Every 2004 or so block, it will check. So 2000, it takes 10 minutes, right? 2004 times 10, about 20 something, times 10 minutes, you know, it's about, you do the math. And that's what it takes to now I'm still on 23 bit and we haven't even come back. I think I'm gonna stop it here. It shows you what it means when we say difficulty level, and you have to show your proof of work that you actually solve the problem. Once you get this nouns, okay, and we know all the other parameters, we could also verify, yes, you did the work or you didn't do the work. So this one is stuck here now. We're almost more than 1 minute on this, and I'm going to stop it here, but that gives us an idea of what we mean by when we say proof of. So Control C, we cut this program off. So we couldn't continue. It's taking more time. We've almost getting to the 2 minutes mark, and it's still looking for it, yeah? So back here, I think that summarizes what we mean when we say, yeah, proof of work. Where exactly am I now? Let me present this. We'll be ramping up in a bit. And 1 minute. So here again, that's the algorithm. I just made a screenshot of the output. That program, that Python program, I'll put it up I'll put it up in the repo. You could take a look at it. And maybe, in fact, I'll put it up there. When you take a look at it, see if you can redo that in Python. No, it's a Python script. See if you can redo it in JavaScript or Golang, whichever one you like. So I'll put up that Python script and do a pull on the repo when I'm done, and pull it down, look at it, and recreate it using JavaScript or Golang, whichever one you've doing our normal, because I'm doing this like a review right now. I don't know why. My internet connection is unstable. Yeah. Okay. My system is hanging now. So I think proof of work, that's where we got to this point. I explained to you in technical terms what proof of work means. So you have the literature already. You have said, but with what I just explained to you, now understand what the literature is saying. Yeah, my machine is just hanging now. So we'll call it quit here. I want to say that tomorrow we are having a guest speaker. He will be taking introduction. I've done the abstract. He will take the introduction, so and explain also what we have there. That's Macmillan from my 2 cents. So please come up tomorrow. You have any question, whatever, for him, if you'll be here tomorrow. And why I also tell you to come up? He's one of the startup we have on the BSV ecosystem. So potentially that's one place we could have internship for some people from this cohort. So make sure you're here tomorrow to interact with him. Yes, so thank you. I'll stop sharing now. And we see you tomorrow again when Macmillan from my 2